Thank you for returning for part 3 of our lecture on moments of inertia by Dr. Emanuel, lecture number 19. So we're doing another example. So this example has a triangle with a density of 1, and it gives us one of the sides for terms of x and y. We need to find m, mass, the vector x, the vector y, the scalar moment of inertia x, and then the vector moment of inertia x. Now we're going to denote moment of inertia vector in bold, okay? I don't have something to go over top of it. Okay, so that we don't get them confused. So this here is our parallel Atlas theorem, which lets us know that the magnitude of x can equal to the vector moment of inertia plus the m, the mass, times the distance squared. Okay, so the first thing we want to do is solve for what? M. Okay, well, let's get m in. Okay, that's the first thing we want to solve for m. And so we have our rho is equal to 1. And so we're going to perform our initial integration, double integration. We go from 0 to 6 and 6 to 0. And 0 to, for our x, for our y, we're going to use this curve. So we're going to solve for y over here, and so that'll be 6 minus x. So that'll be our upper limit. So if we integrate, and like we said, rho is 1, we're just going to get the upper limit, the lower limit will drop out. That's 6 minus x dx. Then if we take the integral of this, of 6, we get 6x, and then we get, that's supposed to be a minus, that's close to it. I don't know why it's on top of it, but that's what happened. Minus our 1/2 x squared. And we're going to evaluate that from 0 to 6. So all we do is just plug that in straight up. We got 6 times 6 is what? 36. We got 1/2. See, there's your minus 1/2. 6 squared is 36. And we got 36 minus 18. Half is equal to 18. So now we know what our mass is. So now we need our mass to be able to find out what our x is. Okay, so we said we wanted to find out our vector x and our vector y. Okay, so if we look at our vector x here, what we see is 1 over m times x dx, x squared. So we found out that that is 18. So it's 1 over 18 from 0 to 6. Okay, and we're going to take our first integration, and this is in reference to y, so it's just going to be x, y. So there's our x and our y, and it's just accepting our upper limit. Our lower limit is dropping out. So it's just 6x times 6 minus y. So if we multiply this x out so that we can have all the terms so we can integrate easily, we have 6x minus x squared. We had our 6x minus x squared. So now we're going to take that, take the integral of that in reference to dx. And so 6x is 3, because it's going to be 1/2 of the value x squared, and this is going to be 1/3 minus 1/3 x cubed. We're going to take it from the limits from 0 to 6, and when we plug these values in, we're going to get 2. So we have x equals to 2. Because it's symmetry, x and y are both equal, and they're both equal to 2. Okay, so next thing we like to look at is the vector, what I said, right? The vector I sub x is the moment of inertia around an axis parallel to the moment of inertia x, that's scalar, but going through the center of mass. And that's what we know is, so go through what? The center of mass. And our center of mass is going to be where? Going to go over 2 and up 2. And that's where our center of mass will be located. That's what we found out here. Okay? So, our next set of equations, which we have in front of us. So remember, this is the moment of inertia of x, but we don't use x, we use the y squared, and z drops out. Okay, because this is only a 2-dimensional. Okay, so now what we're going to do here, we take the integral of y squared, we get 1/3 y cubed. Take the evaluation from 0 to 6 minus 1. Okay, so this was too long, so it didn't carry over. So this is 1/3 from 6, and all we're doing is putting up this upper limit. Okay, and this upper limit is going to be cubed times the 1/3. Sorry about that. So let us use U substitution for this term here. Okay, so to use U substitution, we have 6 minus x for u, and the derivative of this, of the constant, it goes to 0, of the minus 1, it goes to minus 1. So that'll be minus 1 dx. Okay, so for x equals 0, what happens to this equation if we use x equals 0? U equals what? 6. And for x equals 6, then we get this cancel out, and then u equals what? 0. Okay, we have here for our moment of inertia around the x-axis, we're going to be using the minus dx, so we have the minus sign that has to come out, for dx, so that's what we're using for du. Okay, so it'll be a minus du, and then we have u is raised to the 3rd power, and so this would be u cubed. Now, notice we said that the limits go from 6 to 0. Now, if we want to reverse it, this is multiplied by -1, so this can reverse the limits. So the limits will now go from 0 to 6. Nothing else changed. Still got u cubed du. Now, if we perform our multiplication, our integration. So if we integrate, we're going to have 1/4. There's the 1/3. So it's going to be 1/4 times 3 to give us our 1/12. And this will be u to the 4th power. We're evaluating from 6 to 0. Okay, next we look at the 112 carries over, and now we're taking 6 to the what? 4th power, which is 108. Now remember, we found out that m was equal to 18, then x at m equals what? We divide by 6, and you get 6m. To get the vector, okay, we have here the what? The scalar. To get the vector, we use the parallel atlas theorem, where it says that if you have s, the moment of inertia, the scalar is equal to the moment of inertia, the vector, plus m d2. And so we're going to solve for that. Let's solve for the vector, because we already have x, I of x. Now let's solve for the vector, I of x. And so we move the I of x, the md squared, to the other side of the equation. So now we're subtracting that out. And now we have this is equal to 6m minus m raised 2 to the 4th power. So what we can do here, because we do know what our m to the x is, so now when we subtract these out, the 6m minus the 4m, that's what this is. We know what m is, right? We know that d equals 2. We solved that earlier. We already found out that x of m is what? It's equal to 6m. This should be a equal sign. Sorry, I put in a plus sign. So this is minus m times 2 squared. And that's going to give us our vector of Ix is going to be equal to 2m. Thank you. Now we're going to give you some practice problems. This is practice problem number 1. We're going to give you practice problem number 2. This is for a curve, y equals to y squared. Notice your density here that you need to find. We want you to find the moment of inertia for the x, y, and z. Just want to go back one. Okay, here it's asking us to find the moment of inertia around a rectangle. Okay, with uniform density, which has a width of a and b. Express I sub z in terms of the mass. Lamina mass. Okay, here we're asking you to find it around the x, y, z, and then find the moment of inertia of the unit cube in the first octant, assuming uniform density across any coordinate axis. Okay, well, this will be the end of our study. Oh, we have number 4, sorry. We have a 4th practice problem. Find the moment of inertia around the, of x, of the unit cube, whose closest point to the origin is 1, 2, 3, which has density of this time equal to x. So it's a varying density. All right, thank you very much for being part, and we will see you again.